And we're back, and today it's a look at how trigonometry flows from the idea of similar triangles. So this particular screencast shouldn't take too very long because this idea should be familiar to you from high school trigonometry. If your teacher in high school did what I am about to do, stop the video. Got some angle. The angle is theta. The angle is made up of two rays. We choose any point on one of the rays, and we drop a perpendicular to the other ray. So let's pretend that the common point for the rays is A. Let's pretend that the point we picked on one of the rays is B, and let's pretend that the foot of the perpendicular to the other ray is C. Then we define sine of theta as the ratio of BC to AB. And we define the cosine of theta as the ratio of AC to AB. Now, there are really good reasons for that. They flow off of the unit circle. We're not there yet because we're building our geometry, but we will define these ratios in this way. It should be noted that no matter where I pick on this ray, if I were to come out here and pick some other point and drop a perpendicular to C prime, sine of theta would still be as you would expect, and cosine of theta would still be as you expect. Why? Because the little black triangle is similar to the big blue triangle because they share the angle theta and they are each right triangles. So the corresponding sides of those similar triangles are in proportion. Trigonometry depends on similar triangles. Trigonometry is founded on the idea that no matter where I drop the perpendicular, I've got similar triangles everywhere. So sine of theta is sine of theta regardless of the size of the right triangle that contains theta. The ratio of the so-called opposite side to the so-called hypotenuse is the same no matter what the size of the triangle is. Okay, now mind you, we have studied angles from 0 degrees through but not including 180 degrees. So what happens if theta is obtuse? Well, if theta is obtuse, then we say no big deal. Find the supplement and take the sine of that angle. For cosine, we decide take the opposite if theta is obtuse. Now, we have really good reasons for doing that because we look at the unit circle, which is very familiar from high school trigonometry, and we say, here is some angle theta. It's got sine of theta is BC over AB. So then what happens if you bring this over here? What happens if this is the theta instead? Then this is the 180 minus theta. This is theta. You get the same kind of situation going on. If you take the thing that's quote unquote the opposite side and the thing that's the quote unquote hypotenuse, then this ratio is the same as this ratio. So we would expect that the sine of an angle to be equal to the sine of its supplement. Cosine is a different matter, though. Cosine is the ratio of AC to the hypotenuse. What about this guy? This guy is negative. He extends in a negative direction. And because of that, we define cosine of an obtuse angle as the negative of the cosine of the supplement. Well, what happens if theta is 0 degrees? Well, if theta is 0 degrees, then it's really hard to draw a right triangle, isn't it? Because you've got B you've got ray AB equal to ray AC, so there isn't much of an opposite side to work with, and so we define sine of 0 to be 0. Cosine of 0 is defined to be 1, and again, for really good reasons, because if you come back to the unit circle, we remember that the coordinates of x, y on the unit circle are cosine theta and sine theta. So we expect cosine of 0 and sine of 0. We expect that. Now, we haven't built that yet because we haven't done hundreds of years of mathematics that leads to it, but you may remember from high school that that is true. While we're on the topic, let's go copy stuff. Let's copy this stuff and bring it with us. You know from the Pythagorean theorem that AC squared plus BC squared is AB squared. Well, that's phenomenal. What if we divide everybody by AB squared? Well, then something's equal to 1, but what? Well, the ratio of AC to AB, that is cosine of theta, and we have squared everything. The ratio of BC to AB, that's sine theta, and that's squared. So you get the familiar theorem from high school trigonometry using nothing more than the Pythagorean theorem and a couple of trig ratio definitions. There are a couple of things that you should know about trigonometry. You should know that there's this thing called the law of sines. If you're British, it's called the sine rule. And the sine rule says that the sine of any angle of a triangle over its opposite side length is equal to the sine of some other angle in a triangle over its corresponding side length. And that's true for all of the sides in the angles. This is the law of sines. It is traditionally proven using area of a triangle. And so we don't have that in place yet. It can be proven without talking about area of a triangle. I may try to do that when we get together in class. It's one of those nice proofs that breaks down into 3 cases. What if this particular angle is acute? What if it's right? What if it's obtuse? Similarly, there is this thing called the law of cosines, which also can be proven without going to the unit circle. It's where c squared equals a squared plus b squared, and you're thinking, that's Pythagorean theorem! Well, falsetto boy, nice try, but there's this minus 2ab times the cosine of c thing that's floating around. And that works for any angle and its opposite side. So if I had chosen angle A here, then this is a little a, and these two are B and C. The law of cosines can be proven without running to the unit circle. There are ways to do that. I may or may not do that when we gather in class tomorrow. It'll depend on time. Okay, so the big point to drive home is the following. All of trigonometry depends on similar triangles. So without similar triangles, there is no trigonometry. With similar triangles, there's all sorts of good trigonometry. That you should know. Okay, enough. That's trig. We'll go play.